want to take a quick look at just how we solve systems, remind you some things you already know, maybe introduce you to some new things. We'll see. I remember when I first learned, as you may recall in class, I said that I had never seen a matrix before linear algebra. So if I had a system like this, three equations, three variables, I'd be inclined to group I'd look at these first two and say, I'm gonna do something to it. I'm gonna add the two equations together. I'm essentially trying to eliminate one of the variables. So if I add, I'm not sure what's going on here. If I add those two together, I've got 5x, x is minus 6y equals negative 6. Is that what that looks like to you? Not sure why this is looking like it does. But anyway, and then I would say, well, now grab these two equations. So I'd grab these two and say, well, let's add them up. And I'm noticing that I'm adding them just because by adding the minus z and the plus z will go away, and so then I get an equation that just has two variables. So I do the same thing here now. I've got adding the second and third equations. I've got 5x plus 2y it seems to want me to zoom in or out here, but I'm not sure why. Equals, so I'm adding, let's see, those go away, and then I've got 10. Okay. So by combining the first two equations, then in combining the second and third, I have eliminated one of the variables, and now I've just got a system of equations with two variables. Okay, two equations, two variables. Okay, now I want to just eliminate one more. So I'm going to multiply the top one by -1 and add it on to the bottom one. So where am I at? I've got, that would be negative 5x plus 5x is 0. The negative, so that's positive 6y plus 2y is 8y equals positive 6 plus 10, which is 16. So what I've now done is I've gone from three equations and three variables, two equations and two variables, one equation and one variable, and I can solve that one, divide both sides by 8. I've got y equals 2. I would then go back and find x and y. So find x and z, actually. Find x and z by, for instance, plugging in. I could plug the 2 in for y here, solve for x. Once I know x and y, I can go back to one of these. Right? So that's, I'm not going to walk through all the steps, but I told you what the steps are. Essentially finding one, substituting back in, and figuring out what it is, what the other variables are. So you may have several ideas of how you would solve systems. Generally, solution methods that I've seen, one is substitution. I did not do that. Some people would say, well, solve this one for x. Get x all by itself, and then you plug that in here and here, and then you'd have two equations that don't have any x's in it anymore, and you'd solve one of them for y, and then you'd take that and you'd plug it in, and you'd end up with one big old equation with just y's in it. And you'd solve, and then you could work your way back, right? I've chosen to do what's called, that's a 2, elimination. And then we also have the possibility of using a matrix. What's just happened here? Matrix. Now, actually the techniques of using a matrix, at least the initial ones we'll show you, are very much similar to what I did right here. I'm trying to turn my page in my notes here. So a matrix we introduced earlier is the notion of a matrix is a rectangular array of numbers. So I'm going to take this system right here and I'm going to turn it into, not I'm going to turn it into a matrix. I'm going to write down a matrix that I associate with that system. So there's a 1, there's a -7, there's a 1, there's a -10. Those are the numbers from the first row. First equation, then I've got 4, 1, -1, 4, and and 6. So this is a matrix. This matrix may have many, many, many uses. It is not necessarily this system of equations. In fact, it is not this system of equations. However, it is representing for me this system of equations by just keeping track of the coefficients. Right? We will use matrices for all sorts of things: transformations, solving systems, just keeping track of data. I mean, there's lots of things that we would do with matrices. I think initially people get, oh, whenever you have a matrix, you got a system of equations. It's like, well, no, you may not be using that matrix for that. That's what we are using it for now. But we'll do other things. Just keep that in mind. Okay. This is what's called the augmented matrix for that system. Sometimes you'll see, I'm going to do it in a different color. Sometimes you'll see that they'll put a little dotted line down through here just to just separate the coefficients that came from the variables and those that were on the constants over on the other side of the equation. This dotted line has no mathematical meaning. It is simply a visual aid for you to see it. So sometimes it's there, sometimes it's not. It doesn't have to be there to make it an augmented matrix. It's just, what do you want to look at? So, now, I'm going to introduce a method here, which is very similar to the elimination that I did, but it's very methodical, able to be programmed, so your calculator can do these kinds of things. So what we're going to do is we're going to describe row operations. These are called elementary row operations. Elementary row operations. Okay. And they're essentially the things that we can do to equations. For instance, you could take an equation and multiply both sides by a non-zero constant. That doesn't change the solution set. For instance, if you had x equals 2, there's one value of x that makes that true, right? X equals 2. And multiply both sides by 7, so you'd have 7x equal 14. There's still only one value of x that makes that equation true, and it's the same one, right? So I can multiply both sides of an equation by a constant. So I'm going to allow myself to, say, multiply a whole row by a constant. If I multiply this whole row by 2, I'm multiplying all the stuff over here by 2 and the stuff over there by 2. So I'm essentially multiplying both sides of what was the equation by 2. But I'm just keeping track of it here. So I can multiply rows by non-zero constant, and I've got these out of order, but it doesn't really matter. Multiply a row. I'm really looking forward to a new pen here. By that says non-zero constant, right? Now I know that sometimes my penmanship is really bad, but I said it out loud, so you can rewind a little bit and look through that says non-zero, right? So 2. The next thing, you can swap 2 rows. I mean, if you're looking at a system of equations, does it really matter what order you write the equations in? So does it really matter what order my rows are? Because each row is corresponding to an equation. So anyway, that's okay to do. Swap 2 rows. And lastly, that's a 3. That's a 3. I can, what were the kinds of things I did? All right, when I think about what I was doing to solve this thing, like that here to here, I multiplied one by -1 and added it onto the other. And that's exactly the thing that I want to put down here. I want to say that I can add a multiple of one row to another. Add a multiple of one row to another. Those are my elementary row operations. I'm going to use those to solve the system of equations. Okay, so here we go. I'm going to actually, I've got some things over here, and maybe you've been looking at these things as I've been going. I'll come back and explain them momentarily here. I'll hide them for now. So here we go. Where's that matrix? Watch what I can do here. I got 1, -7, 1, -10. I've got, did I put a -10 there? Yeah, I did. Okay. In my notes, I've got it as a +10, but I really want it to be a -10. 3, and 1, 1, 1, 6. So what I'm going to do is just one of these three things, and then another one of those three things, and watch what happens. Right? So first thing I'm going to do is I'm going to swap row 1 and row 3. Right? So going from here to here, I'm going to take row 1 and swap it with row 3. Now, I'm not saying equal. The new matrix is not equal to the first one, but it's corresponding to a system of equations that has the same solution set as the one that I started with. Okay. And then I'm going to, I think, add row 2 I'm going to replace by row 2 minus 4 times row 1. So row 2 minus 4 times row 1. Whoops. Row 1. There we go. So that's going to become this new matrix now. So leave the first row alone. And I'm going to multiply this one by -4 and add it on. 0. Multiply this one by multiply this one by -4 and add it on. Multiply this one by -4 and add it on. -3. Multiply this one by -4 and add it on. -5. Multiply this one by -4 and add it on. So I've got -24 plus 3 is -21. Okay. Now, at the same time, I'm going to replace row 3 by row 3 minus 1 times row 1. So row 3 minus 1 times row 1. So that would be a 0. This one minus that would be -8. This one minus that is 0. This one minus that is -16. Okay. So I now have a matrix which I say is the augmented matrix for some system. What is the system? Well, it's x plus y plus z equals 6. -3y minus 5z equals -21, and -8y equals, that's a 16, equals -16. Right? This right here is really nice because I get very quickly that y has to equal 2. Right? Then I can come back to here. It's just got y and z in it and plug it in. So coming down into there, I've got -3 times 2 minus 5z equals -21. I'm really looking forward to this new pen. -21. So z can be solved for really quickly here. So this is bring a 6 over, divide by the -5, and I think z turns out to be 3. Now that I know y and z, I can plug them back in here, and I've got x plus 2 plus 3 equals 6, which tells me that x equals 1. And there we go. We have a solution. Now, this was an elimination process without having to worry about all the x's and y's. We just looked at the coefficients. All right. This is sometimes called Gaussian elimination, and we will look at this in much more detail on subsequent days. But for now, this is an introduction to how we do it. Systems of equations. You're finding intersection points, right? 2 equations, 2 variables. You're looking at the point of intersection. 3 equations, 3 variables, you're looking at 3 planes intersecting, and you want the point of intersection.